All right, we're going to work Pathways 5.49. It's a really fun problem. It tells us to compute the molar mass of a gas held at 388 torr and 45 degrees Celsius if 206 nanograms of this gas, tiny amount, occupies 0.206 microliters. This is a really fun problem because we got to use a lot of the stuff that we learned in Chapter 5 coupled with some knowledge of these metric prefixes, okay? So the first thing that we always do in these problems is start to maybe make an inventory of what we know, okay? What do I know? I know the pressure is 388 torr of this gas sample. I know my temperature, 45 degrees Celsius. I've also made a mental note that I'm dealing with a Celsius temperature, not Kelvin. That can be important, okay? I know a mass of a material is 206 nanograms, 206 billionth of a gram, and I know my volume is 0.206 microliters. Okay, we have a liters sort of base unit there, which is this micro prefix that we might have to deal with. So we know the pressure, the temperature, we know the volume. Okay, what are we asked? The molar mass. I don't know what the molar mass is. I know what the physical mass of my gas sample is, but I don't know how much a mole weighs. So even though I know the grams of my sample, I don't know what gas it is, so I can't convert to moles. So I don't know how many moles I've got right now, but you know, if I could figure out how many moles of the gas that I had, and I know its mass, I could figure out probably what the molar mass of this gas is. It stands to reason at least, okay? So for problems like this, in general, pretty useful direction to go is to head to your ideal gas law equation, the PV equals nRT relationship, and see if you can work that and make some sense of it to find the information that you need to solve the problem, okay? Now, we already mentioned that I don't know the number of moles of gas, my N, so that's going to be an unknown variable here for sure. Now, we know R is just the ideal gas constant to 0.082. I'm going to exclude the units just for the sake of space, but the units that are attached to this are atmospheres and liters. We need to use atmospheres and liters for P and V, okay? And of course, our T is our temperature. Now, we know when we use this equation, you always need to use the Kelvin temperature. You cannot use Celsius temperature. If you're given a Celsius temperature like you are here, you must convert. Fortunately, we know that the Kelvin temperature can easily be found by taking 273 and adding the Celsius temperature. So 273 plus 45 is my Celsius temperature. That equals my Kelvin temperature, which corresponds to 318 Kelvin, okay? I write that right here, 318. And I'm rocking and rolling. Now I just need my P and my V terms. Now, as I already mentioned, I've got to use atmospheres and liters. I must use atmospheres and liters if I'm going to use this number. So, I'm given that my pressure is 388 torr, which is not in atmospheres. I need to convert. But fortunately, I remember 1 atmosphere corresponds to 760 torr. So I can do the division, and I can convert to atmospheres equal to 0.5105. That's my pressure. Now my volume is a different story, right? I've got 0.206 microliters. This is a tiny, tiny volume. It'll be even hard to measure, as it turns out, right? And I need to convert that into liters from microliters. So I want to ditch my microliter units. All right, well, 1 liter corresponds to 1 million or 10 to the 6th microliters. So I need to divide by 10 to the 6th here, which of course would yield 0.206 0.06 times 10 to the minus 6 liters. That's my volume. So I plug that in here. 2.06 times 10 to the minus 7 liters. And I work the math. Unfortunately, I ran out of space there, so it's a little bit messy. Okay, but it's my pressure in the atmosphere is 0.5105. This is 2.06 times 10 to the minus 7, which is physically equivalent to this. Okay, so I just have to work the math at this point. So if I do so, over on the right-hand side, I'm going to get 26.076 multiplied by n. And then on the left-hand side, let me check my calculator here. Looks like I get 1.0516 times 10 to the minus 7. Okay, so I get that expression, and then I simply solve that for n by dividing both sides by 26.076, and I yield 4.03. 294 times 10 to the minus 9th moles. Notice here I'm not paying too much attention to sig figs, okay? So what have I done here? I have successfully solved for the number of moles of my ideal gas present in this sample given the information that I have, okay? Solve for number of moles that must be present. And we don't know what the gas is, but based on these criteria of pressure, temperature, volume, this must be the number of moles of that gas present. Now, early in the problem, I was told the mass of the gas present, 206 nanograms, okay? If I was to ask you how to compute the molecular weight or the molar mass, you would say what? It's grams per mole? Well, I think I have both of those variables at this point. I know that my sample contains 4.03294 times 10 to the minus 9th moles. So that's 4.03 nanomoles, if you want to say that, right? In addition, that number of moles corresponds to 206 nanograms. Now, when I do my molecular weight, it's grams per mole, right? So I need to convert my nanograms to grams, but I can easily do that by dividing by a billion or 10 to the 9th. So that's 206 times 10 to the minus 9th grams. Now, if I do that math, it works out to 51.07 grams per mole. And if I look back to kind of where we started, it looks like probably 3 sig figs is most appropriate. So maybe I round this to 51.1 grams per mole for my molar mass. And you can see that from the information I've been given in this problem, I've been able to successfully determine the molar mass of this gas must be about 51.1 grams per mole. Might give me some idea as to what that could be if I add up the atoms that make up this gas. Now, this problem was kind of a nice one because you were required to use the ideal gas relationship to really problem solve. And you'll see this type of problem a lot, I think, in the homework and also probably on the exam. Sometimes you're asked maybe to compute the molar mass. If you're given the mass of the gas, the actual physical mass in grams, you can find number of moles, you can compute the molar mass. Sometimes maybe you're asked to find the gas density. In such a case, you'd probably solve for the number of moles and convert that into a grams, and then you'd know what the volume was, so you could do grams per milliliter type of thing if you wanted to compute the gas density. So that could be another thing that you'd have to do. So this problem is nice because it illustrates something that's a little bit different from the types of problems that you might see otherwise. And I kind of characterize this one by being a little bit higher difficulty than maybe some of the earlier problems that we've worked. Because not only do you need to use ideal gas law, what we learned about in this chapter, but you have to use a little bit of your problem solving skills. And sometimes people will struggle with that, but I think if you can help yourself by working a lot of examples, such as this one or other ones that are in your book, and then it becomes a little bit easier, I think, to see the route from point A to point B, because sometimes it can be very difficult to get from point A to point B, and you just kind of run around in circles. So hopefully watching this video is a useful thing for you, but I do have to encourage you to keep practicing this so you can get really good at these types of problems.